Section. Introduction. In recent times, we've seen the rise of large language models, LLMs, like GPT-3, OPT, and PaLM. These models have shown impressive performance in various language tasks. However, they come with a significant drawback. They require a lot of computational power and memory to function. These models can have hundreds of billions or even trillions of parameters, making them difficult to run efficiently, especially on devices with limited resources. Currently, the standard method is to load the entire model into the device's DRAM for it to work. But this approach has its limitations. For instance, a model with 7 billion parameters would need more than 14 gigabytes of memory just to load the parameters in half-precision floating-point format. This exceeds the capabilities of most edge devices. To overcome this, we suggest storing the model parameters on flash memory, which has at least 10 times more capacity than DRAM. During the model's operation, we can smartly load the necessary parameters from the flash memory, eliminating the need to fit the entire model in DRAM. Our approach is based on recent studies showing that LLMs have a high degree of sparsity in their feed-forward network, FFN, layers. In other words, models like OPT and Falcon have more than 90% of their parameters that are zero. We can take advantage of this sparsity to only load parameters from flash memory that have non-zero input or are predicted to have non-zero output. We propose a cost model that takes into account flash memory, DRAM, and computing cores, CPU or GPU. We also introduce two techniques to minimize data transfer and maximize flash memory throughput. 1. Windowing. We load parameters for only the past few tokens, reusing activations from recently computed tokens. This reduces the number of I/O requests to load weights. 2. Row-column bundling. We store a concatenated row and column of the up projection and down projection layers to read bigger contiguous chunks from flash memory. This increases throughput by reading larger chunks. To further minimize the number of weights to be transferred from flash memory to DRAM, we also use methods to predict FFN sparsity and avoid loading zeroed-out parameters. Together, windowing and sparsity prediction allow us to load only 2% of the FFN layer from flash for each inference query. We also propose a static memory preallocation to minimize transfers within DRAM and reduce inference latency. Our load from flash cost model captures the trade-off between loading less data and reading bigger chunks. Optimizing this cost model and selectively loading parameters on demand yields flash loading strategies that can run models 2x larger than the device's DRAM capacity and speed up inference by 4 to 5x and 20 to 25x compared to naive implementation in CPU and GPU, respectively. In the next section, we explore the characteristics of memory storage systems, e.g., flash, DRAM, and their implications for large language model, LLM, inference. Our aim is to elucidate the challenges and hardware-specific considerations essential for algorithm design, particularly in optimizing inference when working with flash memory. While modern NAND flash memories offer high bandwidth and low latency, they can't match the performance levels of DRAM, especially in memory-constrained systems. A naive inference implementation that relies on NAND flash memory might necessitate reloading the entire model for each forward pass. This process is not only time-consuming, often taking seconds for even compressed models, but it also consumes more energy than transferring data from DRAM to the CPU or GPU's internal memory. Flash memory systems perform optimally with large sequential reads. However, this high bandwidth is not replicated for smaller, random reads due to the inherent multi-phase nature of these reads. Each phase introduces latency, disproportionately affecting smaller reads. To circumvent these limitations, we advocate two primary strategies, which can be employed jointly. The first involves reading larger chunks of data. The second strategy leverages parallelized reads, utilizing the inherent parallelism within storage stacks and flash controllers. Crucial to maximizing throughput is the way weights are stored, as a layout that enhances the average chunk length can significantly boost bandwidth. In some cases, it might be beneficial to read and subsequently discard excess data, rather than splitting the data into smaller, less efficient chunks. Motivated by the challenges described in this section, in the next section, we propose methods to optimize data transfer volume and enhance read throughput to significantly enhance inference speeds. Section Summary. Large language models, LLMs, like GPT-3 and PaLM have shown impressive performance in natural language tasks, but their computational and memory requirements for inference are substantial. To address this, we propose storing LLM parameters on flash memory instead of loading the entire model into DRAM, leveraging the sparsity of LLMs to selectively load only the required parameters. We introduce techniques like windowing and row-column bundling to minimize data transfer and maximize flash memory throughput, resulting in faster inference and the ability to run models larger than the device's DRAM capacity. Section: Load from flash. In this section, we're going to discuss how to perform inference on devices where the computational memory is significantly smaller than the model size. This situation requires us to store the full model weights in flash memory. We'll evaluate different flash loading strategies based on latency, which we'll break down into 3 parts: the time it takes to load from flash, the overhead of managing memory with the newly loaded data, and the computational cost for inference operations. We propose 3 strategies to reduce latency when memory is limited. 1. Reducing data load. We aim to cut down the latency associated with flash I/O operations by loading less data. 2. Optimizing data chunk size. We aim to improve flash throughput by increasing the size of data chunks loaded, which should help reduce latency. 3. Efficient management of loaded data. We aim to streamline the management of data once it's loaded into memory to minimize overhead. We're not focusing on the computational aspect of the process, as it's not directly related to our main concerns. This focus allows us to concentrate on optimizing flash memory interactions and memory management to achieve efficient inference on memory-constrained devices. We'll go into more detail on these strategies in the following sections. Our approach takes advantage of the inherent sparsity found in feed-forward network (FFN) models. For example, the OPT 6.7b model shows a significant 97% sparsity within its FFN layer. Similarly, the Falcon 7b model, after being fine-tuned, shows 95% sparsity while maintaining almost the same accuracy. Our approach involves transferring only the essential, non-sparse data from flash memory to DRAM for processing during inference. We use the 7b models as practical examples, but our findings can be applied to both larger and smaller scale models. We choose to keep the embeddings and matrices within the attention mechanism of the transformer constantly in RAM. For the FFN parts, only the non-sparse segments are dynamically loaded into DRAM as needed. Storing attention weights, which make up about 1/3 of the model's size, in memory allows for more efficient computation and quicker access, improving inference performance without needing to load the full model. The ReLU activation function naturally creates over 90% sparsity in the FFN's intermediate outputs, which reduces the memory footprint for subsequent layers that use these sparse outputs. However, the preceding layer must be fully present in memory. To avoid loading the entire preceding layer, we use a low-rank predictor to identify the elements that will be zeroed out after the ReLU function is applied. Our predictor only needs the output of the current layer's attention module, not the previous layer's FFN module. We've found that delaying the prediction to the current layer is sufficient for designing a hardware-aware weight loading algorithm and leads to more accurate results due to deferred inputs. We only load elements indicated by the predictor. We manage neuron data using a sliding window technique. This method involves keeping neuron data only for a recent subset of input tokens in memory. The key part of this technique is the selective loading of neuron data that differs between the current input token and its immediate predecessors. This strategy allows for efficient memory use, as it frees up memory resources previously allocated to neuron data from older tokens that are no longer within the sliding window. From a mathematical perspective, let's denote the cumulative use of neuron data across a sequence of k input tokens as S_AGG, k. Our memory architecture is designed to store an average of S_AGG, k, in dynamic random access memory, DRAM. As we process each new token, the incremental neuron data, represented as S_AGG, k plus 1, S_AGG, k, is loaded from flash memory into DRAM. This practice is based on the observed trend of decreasing aggregated neuron usage over time. As a result, larger values of k result in less data being loaded for each new token. This reduction in data loading is balanced by the memory cost associated with storing S_AGG, k. When determining the size of the sliding window, the goal is to make it as large as possible within the constraints of the available memory capacity. Section Summary. The section discusses strategies for conducting efficient inference on memory-constrained devices by optimizing flash memory interactions and memory management. These strategies include reducing data load, optimizing data chunk size, and efficient management of loaded data. The methodology leverages sparsity in feed-forward network models and selectively transfers essential non-sparse data from flash memory to DRAM for processing during inference. Additionally, a sliding window technique is employed to manage neuron data, selectively loading data for recent input tokens to maximize memory utilization. Section: Improving transfer throughput with increased chunk sizes. We're going to talk about how we can improve the speed of data transfer from flash memory by reading data in larger chunks. We've developed a strategy to increase the size of these chunks to make reading from flash memory more efficient. Let's start with how we bundle columns and rows. In the OPT and Falcon models, the activation of the intermediate neuron corresponds to the use of the same numbered column from the upward projection and the same numbered row from the downward projection. So, we thought, why not store these matching columns and rows together in flash memory? This way, we can group the data into larger chunks for reading. If you look at the figure, you'll see an illustration of this bundling approach. If we assume that each element of the network's weights is stored in a certain number of bytes, this bundling method doubles the chunk size. Our tests show that this increases the speed of the model. We also had a theory that neurons might have highly correlated activity patterns, which could allow for even more bundling. To test this, we calculated the activations of neurons over a specific validation dataset. We found that each neuron's co-activation with other neurons follows a power law distribution. We then identified the neuron that co-activates most frequently with each neuron, calling it the closest friend. Interestingly, each neuron and its closest friend co-activate with each other at least 95% of the time. However, when we tried to bundle each neuron with its closest friend in flash memory, we ended up loading highly active neurons multiple times. This was counterproductive, as these highly active neurons were the closest friend of almost everyone. We're sharing this negative result because we think it could lead to interesting future research on how to effectively bundle neurons and use this for efficient inference. Now, let's talk about how we manage data in DRAM. Even though data transfer within DRAM is more efficient than accessing flash memory, it still has a cost. When we introduce data for new neurons, we have to reallocate the matrix and append new matrices, which can be quite costly. To solve this problem, we've developed a new memory management strategy. We pre-allocate all necessary memory and set up a data structure for efficient management. This data structure includes elements like pointers, matrix, bias, num_used, and last_k_active. Each row in the matrix represents a neuron's up project, row, and down project, column. The pointer vector shows the original neuron index for each row in the matrix. The bias for the up project in the original model is represented in the corresponding bias element. The num_used parameter keeps track of the number of rows currently used in the matrix, starting at 0. We pre-allocate enough memory for each layer to avoid frequent reallocation. The last_k_active component identifies the neurons from the original model that were most recently activated using the last k tokens. During inference, we identify and delete neurons that are no longer needed. We replace the matrix, pointer, and scalars of these redundant neurons with the most recent elements, and subtract their count from num_rows. We then retrieve necessary neuron data from flash memory. The corresponding pointers and scalars are read from DRAM, and these rows are inserted into the matrix. This eliminates the need for reallocating memory in DRAM and copying existing data, reducing inference latency. For the inference operation, we use the first half of the matrix as the up project, and the transposed second half as the down project. This is possible because the order of neurons in the intermediate output of the feed-forward layer doesn't change the final output. All these steps ensure efficient memory management during inference, optimizing the neural network's performance and resource utilization. Section summary. To improve data throughput from flash memory, we increased the chunk sizes for more efficient reads by bundling columns and rows together. However, our attempt to further bundle neurons based on co-activation resulted in loading highly active neurons multiple times, which worked against our original intention. In terms of optimized data management in DRAM, we adopted a pre-allocation strategy and established a data structure to minimize the need for frequent reallocation, reducing inference latency and optimizing resource utilization. Section. Results. We've designed an experiment to improve the efficiency of inference on personal devices. We process each sequence individually, which allows us to allocate a specific portion of DRAM for the key value, KV, cache while focusing mainly on the model size. This method is especially effective when dealing with one sequence or query at a time. We use Hugging Faces transformers and KV caching for our inference process. We test this setup under conditions where about half of the model size is available in DRAM. This demonstrates the practicality of running inference with lower memory footprints. We evaluate our models using two different hardware setups. The first one uses an Apple M1 Max with a 1 TB solid-state drive, SSD, for flash memory. Here, computations are performed on the CPU, and the models are kept in a 32-bit format. The second setup uses a Linux machine with a 24 GB NVIDIA GeForce RTX 4090 graphics card. Here, computations are GPU-based, and models are run in the bfloat16 format. For both setups, we assume that almost half of the total available memory, DRAM plus GPU memory, is allocated for model computations. We use the OPT 6.7b and a sparsified Falcon 7b model for our evaluations. For methods not using sparsity or weight sharing, at least half of the model must be transferred from flash memory during the forward pass. This is because only half of the model is available in DRAM initially, but as the forward pass progresses, the entire model capacity is used. Therefore, any data not present at the start must be transferred at least once. The most efficient theoretical baseline involves loading half of the model size from the flash memory into DRAM. This optimal I/O scenario serves as our primary baseline. To optimize data loading from flash memory, our system uses a 32-thread reading process. This multi-threading approach is designed to enhance data retrieval efficiency, allowing for simultaneous access to multiple data segments. When data is read from flash memory, the operating system typically caches these pages, anticipating future reuse. However, this caching mechanism consumes additional memory in DRAM beyond what is allocated for the model. To accurately assess the real throughput of flash memory under limited DRAM conditions, benchmarks should be conducted without relying on caching. For the OPT 6.7b model, we train predictors with a rank of 128 for the initial 28 layers. To reduce the occurrence of false negatives, the final 4 layers use predictors with a higher rank of 1024. These predictors achieve an average of 5% false negatives and 7% false positives in the OPT 6.7b model. Our predictor accurately identifies most activated neurons, while occasionally misidentifying inactive ones with values near 0. However, these false negatives, being close to 0, do not significantly alter the final output when they are excluded. Using a windowing method with a window size of 5 in the OPT 6.7b model significantly reduces the need for fresh data loading. Using active neurons of the predictor would require about 10% of the DRAM memory capacity on average. However, with our method, it drops to 2.4%. This process involves reserving DRAM memory for a window of the past 5 tokens, which increases the DRAM requirement for the feed-forward network, FFN, to 24%. The total DRAM memory usage amounts to 52.1% of the model's size. Using a window size of 5, each token requires access to 2.4% of the feed-forward network, FFN, neurons. For a 32-bit model, the data chunk size per read is 32 kibibytes, as it involves concatenated rows and columns. On an M1 Max, this results in a latency of 125 milliseconds per token for loading from flash and 65 milliseconds for memory management. Thus, the total memory-related latency is less than 190 milliseconds per token. In contrast, the baseline approach, which requires loading 13.4 gigabytes of data at a speed of 6.1 gigabytes per second, leads to a latency of approximately 2,330 milliseconds per token. Therefore, our method represents a substantial improvement over the baseline. For a 16-bit model on a GPU machine, the flash load time is reduced to 40.5 milliseconds, and memory management takes 40 milliseconds, slightly higher due to the additional overhead of transferring data from CPU to GPU. Nevertheless, the baseline method's I/O time remains above 2,000 milliseconds. Section Summary. The experimental setup focuses on optimizing inference efficiency on personal devices by processing sequences individually and allocating a specific portion of DRAM for the key value, KV, cache. The study evaluates 2 hardware setups, an Apple M1 Max with a solid-state drive, SSD, and a Linux machine with an NVIDIA GeForce RTX 4090 graphics card. The results show that the proposed method significantly improves latency compared to the baseline approach, making it more practical for executing inference with lower memory footprints. Section: Results for Falcon 7B model. We're going to discuss the results we obtained when we applied our approach, which involves minimizing data transfer from flash memory during inference, to the Falcon 7B model. This was done to ensure that our findings are not limited to opt models. The Falcon model we used was a simplified version, which performed almost as well as the original model. We'll present the results we got when we had about half of the model size available for use in DRAM. In the Falcon 7B model, we used predictors of rank 256 for the first 28 layers, and predictors of rank 1152 for the last 4 layers. Our model was set up to reserve memory for a window containing the last 4 tokens. This setup used about a third of the feed-forward network, FFN. In terms of how the memory was allocated, embeddings took up about 4.2% of the model size, attention weights accounted for 19.4%, and predictors required 4%. The active part of the FFN, given our window size, was 25.3%. In total, this amounted to just over half of the model's total size. We also analyzed the latency of our model. Using a window size of 4 required accessing about 3.1% of the FFN neurons for each token. In a 32-bit model, this meant a data chunk size of 35.5 kibibytes per read. On an M1 Max device, it took about 161 milliseconds to load this data from flash memory, and the memory management process added another 90 milliseconds. This resulted in a total latency of 250 milliseconds per token. Compared to the baseline latency of around 2,330 milliseconds, our method was about 9 to 10 times faster. There has been a lot of research into making large language models, LLMs, more efficient as they grow in size. The approaches generally fall into 2 categories: model compression techniques like pruning and quantization, and selective execution like sparse activations or conditional computation. Our work complements these approaches by focusing on minimizing data transfer from flash memory during inference. Our approach is most similar to previous work on selective weight loading. However, unlike other methods that still require loading from RAM, we consider only the cases where the full model can't reside in the whole DRAM and GPU memory on edge devices. We propose a cost model to optimize weight loading, and introduce techniques like neuron bundling tailored to LLMs. To hide flash latency, we build on speculative execution techniques. However, we introduce lightweight speculation tailored to adaptive weight loading. There is a rich body of work on hardware optimizations for efficient LLM inference, including efficient memory architectures, dataflow optimizations, hardware evaluation frameworks, and flash optimizations. We focus on algorithmic improvements, but these could provide additional speedups. Speculative decoding is a technique that uses a draft model for generation and uses the larger model to verify those tokens. This technique is orthogonal to us and can be used for further improvement. In summary, we propose algorithmic techniques to minimize weight loading from flash memory during LLM inference. By combining cost modeling, sparsity prediction, and hardware awareness, we demonstrate a 4 to 5x speedup on CPU and a 20 to 25x speedup on GPU.